As Serge has pointed out, the last lecture will be on February 29th, that's Monday, and all the lectures will be here at this room. Now, what's the aim of the lessons? So they will focus on recent developments in quantum metrology, and the main questions to be answered are the following. What are the ultimate precision limits in the estimation of parameters in classical and quantum mechanics? Does quantum mechanics help to estimate, to have a better precision in the estimation of parameters? Are there fundamental limits? Also a very important question which has had recent developments is, how can we cope with noise within this framework of quantum metrology? Now, we are going to restrict our discussion here to the so-called local quantum metrology. That means that we have some prior knowledge about the parameter to be estimated. That's also useful to estimate changes in some parameter, small changes around some previous fixed value. That's the case, for instance, for gravitational wave detectors that you set up around some phase, and then you want to watch some small changes in phase due to the arrival of a gravitational wave. Now, that's the tentative summary of the lectures. There may be some leaking from one lecture from lecture N to the lecture N+1, depending on the time. So the first lecture today will be a motivation lecture. I'll give you some examples of metrological tasks. I'm going to actually explore quantum metrology within a very specific example, which has to do with optical interferometers. I'll also derive, if there is time, classical bounds on the precision. That means the classical Cramer-Rao bound, and I'm going to introduce the classical Fisher information. Okay. Now, in lecture 2, I will extend the Cramer-Rao bound and the Fisher information to quantum mechanics. I'm going to derive an expression for the quantum Fisher information for pure states, pure quantum states. I'm going to discuss the role of entanglement in increasing the precision of estimation. And I'm going to apply this methodology, this theory, to atomic interferometry and also to weak value amplification. And in particular, I'm going to show you that quantum metrology allows one to give precise bounds and understand the meaning of weak value amplification. Is it useful or not? In lecture 3, I'm going to introduce noisy quantum enhanced metrology. There is actually a general framework for dealing with this problem. And I'm going to apply this general framework to optical interferometers, force estimation, and atomic spectroscopy. And then, in the last lecture, I'm going to discuss at length the relationship between quantum metrology and the energy-time uncertainty relation. That will lead us to the so-called quantum speed limit, which is related to geometry of quantum states. So we'll do some geometry here also, but in Hilbert space. And then we are going to generalize this energy-time uncertainty relation to open systems for which the energy is not, of course, well-defined. So it should be replaced by something else. And we are going to apply this generalization to atomic decay and dephasing. Now, in these notes that you have got, there are some references. There are 2 pages. It's not extensive, so these are just some examples of references that might be useful to you. These are general references in quantum metrology, and these are specific references related to our work, which will be discussed along this course, along these lectures. So we start with Leçon 1, and the idea here is to give you a general introduction on parameter estimation and classical limits on precision. Now, parameter estimation is actually important for several areas of science. We might be interested in, for instance, in estimating the depth of an oil well this example was more valuable some years ago. It's less valuable now. In order to do that, we could send, for instance, sound waves and look at the reflected waves, and with that estimate the depth. So the sound waves are the probe now for estimating this depth. We might be interested in the time duration of some process, or in estimating weak forces or small displacements by using, for instance, laser beams that are scattered by some mirror, and then by measuring this pointer here, you can estimate a small force, a small displacement or weak force. Of course, we are also interested in estimating phase displacements in interferometers, and a very nice example is what's happening at the Laser Interferometer Gravitational Wave Observatory. That's the LIGO project. You see here a paper that shows that they are using squeezed states. We are going to see how that works here. And they get enhanced sensitivity by using squeezed states. Or we might be interested in evaluating the difference in frequency of some atomic transition due to a small displacement of the atom in the gravitational field. And you see that in this experiment done in Wineland's group, the precision in the measurement of the frequencies is actually very high. So this is 10 to the minus 17. That's the relative change of frequency due to the displacement of an atom in the gravitational field. So in LIGO, we have also some extremely high precision nowadays. You have here the interferometer in Livingston, Louisiana. This is the one in Hanford, Washington. When some gravitational wave comes, one of the arms of the interferometer gets shorter and the other one gets longer. And therefore, there is a differential displacement, which is of the order of 10 to the minus 19 meters. And the corresponding differential strain sensitivity for a arm length of 4 kilometers is 3 times 10 to the minus 23. So it's an amazingly high precision. This is a signal which was obtained some time ago, which shows the strain sensitivity as a function of frequency when you have a typical noise without squeezing. These are the red curves here. This is the short noise limit, the dashed line, and the blue curve corresponds to the squeezing enhanced sensitivity. And at that time, there was a gain of 2.15 decibels due to the use of squeezed states. Now, of course, here in these interferometers, one is interested in detecting these ripples in space-time associated to with gravitational wave. But there are other ripples that have been produced recently. In fact, there are ripples that perhaps a gravitational wave was detected by looking at coincidence between this interferometer and this one. This is not confirmed. The group that is dealing with that just says in a very correct way that is analyzing the data, but they got very sensitive data, and people say that maybe it was observed. So all of that shows that the sensitivity in this kind of experiment is so high that quantum mechanics, in the sense of typically or highly quantum mechanical states, play an important role in these devices. Now, there are many other examples. I'm not going to go into detail into all these references, but that's just for your illustration. You have that in the material that was distributed. So one may be interested, as I mentioned before, in phase resolution, and there are many experimental recent papers on that. We might be interested in increasing the resolution of atomic clocks beyond the classical limits. And again, we have here several examples of experiments made with atomic clocks beating the quantum limits. We might be interested in measuring very small magnetic fields, and here they are all experimental papers about increasing the sensing resolution of weak magnetic fields. So there are lots of experiments on that, but there are also some very basic questions that are related to quantum metrology, some conceptual questions. And they have to do with the meaning of relations like this one, the time-energy uncertainty relation, or yet the number-phase uncertainty relation. These relations have been, since a long time, sometimes been attributed to some Hermitian operators that should be attributed to time and phase. The idea is that if you have two non-commuting Hermitian operators, then from that you can derive an uncertainty relation. And since this one involves time, there was this idea of attributing time to, associating time to some operator, the same here. What I'm going to show you is that using quantum metrology, we will see that we can derive relations like this without associating a Hermitian operator to time and phase. So for us, time and phase will be parameters, and we are interested in the estimation of these parameters, in the precision of estimation, and the relation we get is actually looks very much like this one, actually, but of course, in that relation, time will not be an operator, it will be just a parameter. So that's a conceptual point which we are going to stress also along this course. Now, let me start with a very simple example. Not so simple, actually, as we are going to see. That's about optical interferometry. So we have this kind of device. We have here a beam splitter. These are mirrors, another beam splitter here, and then we can detect the fields coming out in this path or along this path here. Now, if initially you have some field coming in along this path, that's A in, and suppose the two phases are equal, so there is no phase difference between the two arms, then in this setup, this field that comes from this path here goes out along this path. The same with B. B coming here goes out along this path. However, if there is some phase, you can get interference between these two, another kind of interference between these two fields, and then you can get a more complicated situation. Now, that is described in the following way. We can describe that by this matrix product. These are the incoming fields. This is a matrix that corresponds to the first beam splitter. This is the dephasing due to these two dephasing devices here in the two arms. And that corresponds to the second beam splitter. And this gives us the outgoing fields in terms of the incoming fields. It's easy to see that if you set up phi 1 equal to 0 and phi 2 equal to 0, so there is no dephasing here, then the product of these two matrices gives you 1, which means that A out is equal to A in, and B out is equal to B in. Okay? Now, so this whole setup can be described in this way. Now we can multiply these matrices, and if we do that, we get then this expression, which just tells again that if phi is equal to 0, this is the unit matrix, so A out is equal to A in, B out is equal to B in. And now we have transformed the fields into annihilation operators. So this is now a relation between the incoming annihilation operators for modes A and B, and the outgoing annihilation operators for modes A and B. This annihilation operator annihilates photons in mode A, so that if you apply A to a state with n photons, you get this relation here. You get a state with n minus 1 photons. And on the other hand, A daga A applied to n, this state with n photons, gives us the number n times the state, which means that A daga A is the number operator in this case. Now, we neglect this overall phase here, so for us what really matters is this transformation. And what we are going to do that is to introduce new operators. These are called sometimes Jordan-Schwinger transformation, which will allows us to analyze the Mach-Zehnder interferometer in terms of angular momentum operators. The advantage of that is that unifies the treatment of different kinds of systems. So the treatment of optical interferometers will be formally the same as the treatment for atomic interferometry or for magnetometry. Okay, so it's the same thing. So I will define in terms of these operators angular momentum operators, and they are defined in the following way. Now, this analysis was made in this classical paper here by Urke, McCall, and Clauder. That's from 1985. A recent review was published in Progress in Optics, 2015. It's a very nice review. I recommend it to you. And in fact, in this part of the lecture, I'm going to follow this paper and this paper here. Now, so these are the angular momentum operators that are defined in terms of the operators A and B. It's easy to show that these operators defined in this way satisfy the usual angular momentum commutation rules. Furthermore, if you square the angular momentum operator, that's the sum of jx squared plus jy squared plus jz squared, you find that it's given by this expression, or n is just the total number of operators. So it's the number of photons in mode A plus the number of photons in mode B. So you see that J is indeed an angular momentum operator. It satisfies all the properties. And we can show that the transformations of operators A and B along the device, so as they go through as the field goes to the beam splitter, the two arms, and then the second beam splitter, can be considered as rotations in spin space or in angular momentum space with transformations like this, where this operator is a typical rotation operator associated with this angular momentum operator J, and N is some directions, is a direction which points along the axis of rotation. And the correspondence between this transformation and the previous device is the following. For the beam splitter 1, that corresponds to a rotation along the x-axis by pi over 2. The beam splitter 2 corresponds to a rotation along the same axis with minus pi over 2, or vice versa. Okay, so one is the inverse of the other, so that the product of the others gives us 1, as expected. And then the phase delay is associated with this operator here, which is an exponential of jz, which produces this differential phase in both arms. So that's the idea. So now we can write down the full transformation, beam splitter 1, then the phasing, then beam splitter 2, along the optical interferometer. So we have this expression here. So this is homework for the students here, okay? Show that. This is the first beam splitter, the phasing, second beam splitter, and if you multiply all that, you get this matrix here. And you see that this matrix here corresponds to a rotation around the y-axis, because you see Ji does not change, okay? So the three transformations are equivalent to this rotation around the y-axis. And the state, on the other hand, transforms like that. So you see that's the incoming state of the field. We apply the first rotation, then the dephasing, then the second rotation, and you get the outgoing state. So this is the basic formalism we are going to use. And based on it, we are going to derive now an expression for the uncertainty in the estimation of the phase for measurements of the difference in photon numbers at the two outputs of the interferometer. Now you see, if you are interested in the difference in photon numbers, that means that we are going to measure Jz, because Jz is the difference between the photon number operators in A and B. Okay? So that's our aim, to measure the average value of Jz, and we want to know what's the uncertainty in this measure, which will depend, of course, on the variance of Jz. Now, so I'm going to give you several examples of that, but first some general expressions. You see, that's what we want to measure, because this difference in the number of photons is equal to 2Jz. On the other hand, you see, if you look at this expression here, that's really a Heisenberg picture expression. You see, you have here the operator, the outgoing operator, in terms of the incoming operator. So in this kind of point of view, we are letting the operators develop in time, evolve in time, while the state remains fixed. Okay, that's the so-called Heisenberg picture. Now, if you are interested in measuring the average of the outgoing operator. That's equivalent to measure or to calculate the average of JZ in the incoming state. Okay, because now we go to the Schrödinger picture, if you want. Okay, so we can write that the average of JZ in the outgoing state is equal to the average of JZ out in the incoming state, and that's equal to this expression here. Okay? So you see here just the rotation around the y-axis. The z component of the angular momentum for the outgoing field is a combination of the incoming z component and the incoming x component, and that's just a rotation around the y-axis. Okay? Now, the variance of Jz can also be calculated in the same way. So again, the average of the variance of Jz in the output state is equal to the variance of Jz out in the incoming state, and that's given by this expression, okay? Where this is the covariance, which is defined in this way. So these are the basic expressions. You try to derive them later. It's just straightforward. You calculate from the matrix transformation. And from that, we want to estimate the error, the precision of estimation through an error propagation formula. So we write then that the uncertainty in phase is given by the variance of Jz divided by the derivative of the average of Jz in the outgoing state with respect to phi. Okay? So for the moment, that's going to give us the precision of estimation. Then later on, I'm going to give you some more general expression which will give you the ultimate precision limit. Okay? Now, delta phi here is just the square root of the variance. It is the standard deviation, and the same for delta Jz. Okay? So that's the basic equation we are going to use. And remember, we are going to calculate for each situation the variance or the variance of Jz out from this expression, and the average of Jz in the outgoing state from this expression here, which we are going to need in order to differentiate with respect to phi. So that's what we are going to do. From now on, we just have to turn the crank of the machine for different incoming states. And that's what I'm going to do now. Okay. So first try. Let's consider that we have a Fock state injected in the A mode of the interferometer. So the incoming state is this one. N photons in mode A, 0 photons in mode B. Again, these are the definitions of the angular momentum operators in terms of the annihilation and creation of operators of modes A and B. And you see that if we start with this initial state, it is an eigenstate of Jz and J square. In fact, if you apply Jz to that, you just find this expression here. It's trivial to see, since Jz is given by this expression. And J square, which is given by n over 2 times n over 2 operator plus 1, applied to this just gives us the corresponding photon numbers. So J square is given by that times the state. I forgot the state here. So this state is an eigenstate of J square. Okay? So you see that it's actually an eigenstate of J square and Jz that corresponds to the maximum possible component of Jz. So I can write this state here as the state Jj. Now, it's easy now to calculate all the quantities we need in this state. So we find that these expressions for the average of Jz in state in, the average of Jx in state in, and the variance of Jz and Jx. And we find that the covariance is equal to 0. Actually, it's going to be equal to 0 in all the states we are going to consider in these examples. Now, so remember, we have these expressions here. Now, this is 0 because of this. This is 0 because the covariance is 0. And the variance here of Jz is also equal to 0 because this is an eigenstate of Jz. So the expression simplifies. And now we can calculate the uncertainty in the phase through this error propagation formula. And it's equal to that. So it gives us 1 over square root of n. And that's called the standard or short noise limit for optical interferometry. Okay? So with n photons, we get that. Now, geometrical interpretation of this result. We see our initial state is a maximum angular momentum state, which is state Jj. So we can represent it by a cone. The length of this vector here is square root of j multiply j plus 1. Remember that j is equal to n over 2. The projection on the z-axis is just the jz, the value of jz, which is equal to j. And from these two expressions, from this triangle here, we can calculate the radius of the base of this cone. It's just the square root of the square of this length minus the square of this length. So you have it here. So it's square root of j. So this radius is equal to square root of j. Now, let's apply to this initial state the sequence of transformations of the beams of the optical interferometer. So first we have a rotation around the x-axis. Then we have a dephasing, which is a rotation around the z-axis. And then we have another rotation in the opposite direction around the x-axis. So this cone goes to this plane here. The axis of the cone goes to the xz plane. So we have a cone like that. Now you see that if you want to detect this phase displacement, which is now projected here, you must have it larger than the angle defined by this cone, which is this phi minimum here. And this angle, if j is large enough, the tangent of this angle is just square root of j divided by j. So you can write that the minimum angle is square root of j divided by j. So this is 1 over square root of j, and this is of the order 1 over square root of n. Okay? So that's the geometrical way of understanding the short noise limit in this case. Okay, now let's see if we can go better than that. So let's try optical interferometry with coherent states. So now we have a state like that, a coherent state in one arm, no vacuum in the other arm. And just to fix the notation, that's the usual pretext to remind you. A coherent state is an eigenstate of the operator A. The eigenvalue is in general complex. And the average number of photons in the state is given by this expression here. It's just the magnitude of alpha squared. Okay? So if you want to think about a quasi-classical field, magnitude of alpha would be the amplitude of the complex phasor corresponding to that field, and phi is the phase of that phasor. Okay? Now, we define the quadrature operators in the following way. This is the quadrature Q. This is the quadrature P, corresponding to any angle theta. P is Q of theta plus pi over 2, so P is orthogonal to Q. And we can show very simply from these expressions that they satisfy this commutation relation. Now, it follows then that the corresponding standard deviations in this coherent state for these two quadratures are given by 1 over square root of 2. And if you multiply them, you find that the product is equal to 1 over 2, which is the minimum possible uncertainty between the product for the product of the two standard deviations. So the coherent state is a minimum uncertainty state. It's represented here as a circle. We have here this width of the coherent state, delta Q, now projected in this real axis here. It's 1 over square root of 2. That's the phase of the coherent state. The amplitude along this direction is called the quadrature amplitude. The amplitude along this direction is called the phase quadrature. And this eigenvector alpha of the annihilation operator can be written in this form. Okay, so let's try now with a coherent state. Again, you see, you just turn the crank. Initial state is like that. So we calculate all the relevant quantities. They are here. Write down the equations we had before, the general equations that express the outgoing values of the average of Jz and the variance of Jz with respect to the incoming values. Remark that in this case, these two are 0, but you see it's important that the variance the outgoing variance of Jz depends on the incoming variance of Jz and of Jx. And now you get this expression for the uncertainty. It's just given by this one. And now you see, first remark, that it's different from the previous one. So that shows that the uncertainty depends on the incoming state. But it also shows that it depends on the angle phi. So in fact, you see that the precision is better at two operating points, phi equal to pi over 2 or phi equal to 3 pi over 2, and sine of phi is equal to 1 in the region from 0 to 2 pi. And these 2 points actually correspond to the maximum variation of Jz out with respect to phi. So you see we have a cosine here. So the maximum speed of variation of Jz is here and here. So that means maximal sensitivity of the average of Jz with respect to small changes of the parameter. Okay? So, so these 2 remarks are important. Bound depends on the incoming state, and also it depends on the operating point. And since it depends on the incoming state, we might perhaps hope that it's possible to get something better than that, than the short noise limits, by using different states. And we are going now to see what happens if we use a combination of a coherent and a squeezed state. Now, my colleagues who know that will allow me to explain that to people who don't know it, okay? So I just want to introduce squeezed states here. So a squeezed state is a minimum uncertainty state that results from a scale transformation on a coherent state. So you compress one side, and at the same time you increase the length of the other quadrature, of the orthogonal quadrature. So it's something like that, okay? This was a coherent state, but then we compressed it in this direction, and it got elongated in this one and shortened in this one. More formally, a squeezed state can be obtained from a coherent state by applying this transformation. You see it's a nonlinear transformation involving the operators A and A dagger. And this quantity here, psi, is a complex number which can be written in this way. Now you see that if psi is real, that means that theta is 0, which means that the long axis of this ellipsis here is vertical. Okay, so that's theta equal to 0. And if that happens, this uncertainty here is along the real axis here. So we can write that delta Q is equal to e to the minus r over square root of 2, and for delta P, something similar, but with exponential of r. So the larger r, the more compressed is Q, and the more elongated is P. Okay? Now, for metrology, in fact, the squeezed vacuum states are more relevant, so I'm going to use this expression here, and that's, in fact, a squeezed vacuum state, a squeezed coherent state to be displaced with respect to the origin in this picture. We can show that the average number of photons in the squeezed vacuum state is given by this expression here. So you see a squeezed vacuum state has an average number of photons different from 0. So it's not vacuum in this sense, it's a squeezed vacuum. And in this average number of photons increases as the compression factor increases. That only tells you that we need energy to produce a squeezed vacuum from vacuum. Now, so what's the idea now? Now we start with this state here. So it's the product of a coherent state times a squeezed vacuum state. So we inject a coherent state into one arm of the interferometer and a squeezed state in the other arm. And we assume for simplicity that Xi is real, so that amounts to fix a direction in phase space. So our squeezed state is like that, okay? And we can, again, turn the crank and calculate these quantities. Now, remember that the variance of Jz in the outgoing state depends on the variance of Jz in the incoming state and also on the variance of Jx in the incoming state. Now look at the variance of Jx here. And you see this factor here depends on the squeezed state. It's clear, huh? Because if you set r equal to 0, no squeezing, this vanishes because hyperbolic sign of 0 is 0. Okay? So this is the contribution from the squeezed state. Of course, there is another contribution here too. Now, you see that this contribution is a good one because it has the minus sign here. So it reduces the variance of Jx, and therefore it will reduce the variance of Jz out, and that will help to increase the precision in the estimation of phase. Furthermore, for the same number of photons of the incoming coherent state, it's clear that we get a better result if alpha is real. Okay? Because, so it means that instead of using a coherent state here, we are going to have it here. Okay? So that's the best situation. And now if we replace this into the previous expressions of Jz out and the variance out of Jz, and we do this choice of the phase of alpha, we find this expression for the variance of the phase looks complicated, and in fact, in general, it can be analyzed numerically. But on the other hand, if you have many, many photons, we can do something analytical here. And the idea is the following. So this is, again, the expression. Look at this expression. You see that the optimal operating points are cotangent of phi equal to 0, and phi is equal to pi over 2 or 3 pi over 2. You see that comes from cotangent phi equal to 0. Why? Because this will make this term here in the square root to vanish, so it will decrease the variance of phi. So we should try to work around these phases here. If we do that, then we have this expression for delta phi. And now we consider that the average number of photons is much larger than 1. And we assume that the squeezed vacuum carries approximately square root of average of n over 2 photons. So now you see, that's much less than the average number of photons, because it's square root of the average number of photons. So that means that the squeezed state has a number of photons which is much smaller than the number of photons of the coherent state. Okay? Now, we do that, and we use that in this limit of high photon number, large photon number, sine hyperbolic square can be written like that, and this is approximately equal to that. I leave that to you to show. And then we can calculate this uncertainty in the phase, and we find then that is given by this expression. Now, so this is better than the shot noise. It's still, we might still wonder if it's possible to do better, and we are going to show that it is indeed by using a different incoming state. But on the other hand, the state that I'm going to show you next is tougher to produce, much harder to produce. So this is the preferred state actually for the LIGO interferometer. And this was a very nice contribution, as I mentioned in the previous slide, by Caves in 1981. Okay? Now, so let's try to do better than that. And I'm going to do the following. I'm going to use, again, the angular momentum representation. And a general n-photon two-mode state can be written in the following way. Now, let's try to understand this. Of course, this is angular momentum, so m goes from minus j to j. I set j equal to n over 2, where n is the total number of photons in the state. That means that we are considering states with fixed number of photons. Okay, it's not like a coherent state. And Jm corresponds, say, in the mode occupation notation to this state here. So just to make things more clear, suppose we set m equal to j. Now then this is 0, this is j plus j, which is n, so we recover the state n0 that we considered before, a Fock state coming into one of the ports of the interferometer. Now, we assume in the following that n is even, and we are going to consider this state here, which is j0 plus j1. You see, in terms of angular momentum, these two states have very low JZs, okay? So they will be represented by, these are states that are very close to the equator, and I'm superimposing these two states. Now J0 plus G1 can be written in the mode occupation notation in this way, okay? So this is completely equivalent. You see if you look at this correspondence here. Okay? Now again we calculate all the relevant quantities, and we then estimate the precision. So, so this is the expression we had before. The covariance term I have set to 0, and oops, yeah, and then I calculate the estimation here, and it's given by this expression. Now again, you see that if we have a large J, so large number of photons, the optimal operating point is at phi equal to 0, because then this term will vanish, and this is a bad term because it's in the numerator, and at the same time, this term here is going to vanish, but this term here will be maximal, because cosine of phi is equal to 1, and this is a good term because it's in the denominator. So it will have to decrease to increase the precision. So now for large J, this becomes equal to that, and that's proportional to 1 over n, when n goes to infinity. Okay? So now we have got a limit which is much better than the previous ones. And of course, this result is much better than the combination of a coherent plus squeeze state input, but this state is difficult to realize with photons. So that's why the other one is used. Now we can also make a geometrical interpretation of these results. See, remember these values here for this superposition state. Now the average of Jz is equal to 1/2. So if G is very large, that means that this is a cone. It's a very narrow cone, okay? Because the average of Jz is small. Also, the variance of Jz is equal to 1/2. So the width here is very tiny, comparing to the side of the cone. The side of the cone is given by this expression, the average value of Jx. So it increases with n as J increases. So this side of the cone has this length here, which is of the order of J over 2. And now we apply the three operations we had before to this cone. So first the rotation around the axis x by minus pi over 2, then the dephasing by phi, then another rotation by pi over 2. And you see that this new cone is distinguishable from the previous one if this phase is of the order of the width of this cone here, which is 1 over J. Okay? Actually, it's what I have calculated is just delta Jz, which is this width, divided by the side of the cone, which gives us something of the order of 1 over J, and J is proportional to n. So you understand now that the Heisenberg limit is related to the fact that we have a squeezed cone here, which makes the precision in the determination of the phase better. Okay? So now, other interferometric tests that follow the same formulas are, for instance, yes?
So is it, I thought it was the same result in the precision of delta phi for a two-mode squeeze state instead of this.
Okay, actually, you see, for an interferometer, if you are saying, suppose you put two squeeze states in the two modes, that's not a good solution for the interferometer, I mean, for the gravitational wave interferometer. That was shown by Caves, actually, that it's better to have a coherent state in a squeeze state. And the reason for that is that if you put a second squeeze state instead of coherent state, you increase the contribution of radiation pressure, okay, which is bad for gravitational wave interferometry. And this argument you can find in the paper by Caves in 1981. Okay? So, but it's a good point. Now, so we now go to Ramsey interferometry, the same thing. We now are dealing with a two-level atom, excited state E, ground state G. we have initially a state, an excited state, which we represent by this arrow here. Then we apply a rotation around the x-axis, so we get this state. Then a dephasing, and then we get this state here. And then another rotation around the x-axis. This rotation is along the same direction than the other one, but it doesn't matter. So we get this state. And now we calculate the difference in probabilities. We repeat the experiment several times, and we calculate the probability of finding the system in the ground state minus the probability of finding the system in the excited state. We measure that, and that's related to the average of Jz, which is related to cosine phi. Okay? So you see, it's the same kind of technique, and from that, of course, we can calculate the uncertainty, and it should not be surprising that for this procedure, we should expect the uncertainty in the phase to scale like 1 over square root of n, where n is the number of atoms that you send through the Ramsey interferometer. Of course, the analogy breaks at some point because you don't have states here with indefinite number of atoms. However, you can produce special atomic states which lead to better precision and even to Heisenberg scaling. Now, this could be entangled states. I'm going to discuss that in lecture 2. But here I just want to point out that you can produce squeezed atomic states. So you first take n atoms, you put them in the ground state, then you apply this transformation. This involves some nonlinear interaction between the atoms. And you can see that this is very similar to the squeezing transformation we had for the field, which involved A dagger square and A squared. So it's analogous to that. So if you apply this transformation to the ground state, instead of having a circle here, which would be like a coherent spin state with uncertainties in Jx and Jy equal, you can decrease the uncertainty in one direction, increase the uncertainty in the other, and now you proceed to the sequence of transformations. First pi over 2, then dephasing, then pi over 2 again. And you see that when you make this final pi over 2 rotation, this squeezing axis is rotated as well, so that along z you have this smaller uncertainty that corresponds to the short axis of the ellipsis, which will give you higher precision. Okay? So the same idea. Magnetometry, again, the same idea, but I'm not going to go over that again. Okay? So it's quite general formulas and quite useful formulas. However, we might be critical, and we should be critical of everything I have done so far. First, we have just tried some states. We have not obtained some ultimate precision limit, because we're just trying the states. And we don't know if even the measurement procedure we are using is the best one. Maybe there is another measurement procedure that might lead us to a better limit. So in order to look at these things, we have to develop a general estimation theory. And this general estimation theory, the purpose of that is to answer precisely these questions. What is the ultimate limit for a given input state? What are the best states that we can use for getting better precision? What is the best measurement procedure? Okay? So we are going to discuss that, and in fact, this is the aim of this series of lectures, to develop and apply to some examples a general estimation theory. Okay? And moreover, everything I have told you up to now is related to closed systems, unitary evolutions. But of course, nature is not so fine to us. Systems interact with the environment. So we need also a theory that will deal with open systems, and I'm going to discuss that here too. Now, what is the general approach to parameter estimation now in classical and in quantum physics? We have some dynamical process here, which depends on some parameter that we want to investigate. We prepare a probe in some initial state. The probe interacts through this dynamical process, and the interaction depends on the probe you want to investigate. And then we detect the final state of the probe. We choose a suitable measurement. And then for each experimental result, J would be a set of experimental results. We associate some estimation of the parameter. So that's the idea. Now we need a merit quantifier. And this merit quantifier can be defined in more than one way. The most common one is this one. So this is the standard deviation of the estimator with respect to the true value of the parameter. Now, we are going in all these lectures deal with the situation in which we have an unbiased estimator. That means that the average of the estimator is equal to the true value of the parameter. And that's true not only for the true value of the parameter, but also around some region around the true value of the parameter. So the derivative of the average estimator with respect to x, evaluated at the true value of the parameter, should be equal to 1. Okay? We call this an unbiased estimator. A very bad unbiased estimator, perhaps one of the worst, is the following. You don't look at the measurements and you say the value of that parameter is 2. Now that's clearly biased, and we want to punish this kind of thing. There are ways of doing that, of punishing bad estimators. I'm not going to discuss that here. Okay? So I'm going to assume that these conditions are well satisfied. Okay. Guessing the time is better because at least you'll be right 2 times during 24 hours, right? But that's also a biased estimator. Okay? Now, so an important thing is that, of course, because of these conditions, then this expression here becomes the variance of the estimator with respect to its average. Okay? It's no longer the distance with respect to the true value. It is that true. It is that 2, but we can replace it just by the variance of the estimator. Also, of course, the estimator depends on the experimental data, as this diagram makes clear. So, a long time ago, actually, Kramer and Rao had some ideas about that, Fisher too. And Kramer and Rao derived an interesting bound for unbiased estimators. They showed, and we are going to show that here, that the standard deviation in the measurement of x is bounded below by this expression here, where n is the number of repetitions of the experiment, and fx is this function here, which is called Fisher information, while this pj of x is just the probability of getting an experimental result j for a value of the parameter equal to x. Okay? So this comes from the experimental data. Okay? Now, of course, if you have the experimental data and you have some model for the system you are measuring, which depends on the experimental data and on the parameter, by measuring and getting this expression, you can find out what the value of the parameter is. Okay? So that's the basic idea. You need some model. Okay? Now, so this is an expression for discrete measurements. For continuous measurements, you have this expression instead. It's an integration, where psi here are the measurement results. And of course, this all means that you have to average this expression here, which is squared, for all experimental results. Okay? This is an average over all experimental results. Now, so let me derive the Kramer-Rao bound with 2 slides. So let's consider first the probability distribution corresponding to a single output. That means a single experimental realization. We are not repeating the experiment. Okay? Now, and I'm going to assume the estimator unbiased, so the average of the estimator should be equal to x. Now I start with this equality, not inequality, with this equality, which is very trivial. Okay? So you see, this just tells us that, okay, if we integrate over psi, x does not depend on on psi, and this will just give the average of x, which is equal to average of x estimator, which is equal to x, so this gives us 0. Okay? So just correct that, that's an equality. So I start from that. Now I differentiate this with respect to x, and I get the following. So this is the derivative of a product. First I differentiate this term here, and then I differentiate this term here. Now this estimator depends on the experimental data. It's obtained directly from the data. So the derivative of that is just -1. So I get a minus p here, which is integrated over psi, so that gives it -1, which I put to the other side. So after doing that, I get this expression here. Now, you know, this looks like a scalar product, right? This is a measure, the distribution probability times the psi. This is one of the terms of the scalar product. This is the other term of the scalar product. So we can apply here the Cauchy-Schwarz inequality, which means that the square of this expression here is smaller or equal than the average of the squares of these two terms here. So this means that if this is true, then this is true here. This is now the average of the square of that. That is the variance of x estimator. And this is the average of the square of this. And this should be larger or equal than 1. And from that, we get trivially the value of this variance here, which is given by this expression. Okay? Now, this is the Kramer-Rao relation for one realization. I repeat it here. And the denominator in this expression is just the Fisher information, which can be written in different forms. Okay? So this is just equal to that. It's just the average of the square of this function here. Now, this, if I differentiate the logarithm, this gives me that. And it's easy to show that this can also be written like that. And I would like to stress this expression here because it's the easiest to work with. Okay? In fact, it will be useful for us in the following. So that's the famous Kramer-Rao relation, and that's the famous Fisher information. Now, suppose now we have several identical and independent measurements, so that we now have a probability distribution of experimental results, which is the product of these independent distributions corresponding to n measurements. And let's call f of x the Fisher information corresponding to one of the measurements. Now, you see the Fisher information corresponding to all these measurements, I call it fn of x, and it should be equal, according to the previous slide, to the average of this expression here, the second derivative of the logarithm of this whole distribution here. So I'm just using this expression here, okay, for the Fisher information. So and I use it for this p, which is the product of all of them. Now you see, this expression is very easy to deal with because log of the product is sum of the logs. So immediately you see that this gives us a sum of Fisher informations corresponding to each experimental realization. And since they are equivalent, they are identical, this is just n times the Fisher information for a single realization. Okay? So the scaling behavior comes out immediately from that. And that's what is called the additivity property of the Fisher information. And then it follows from this that the Kramer-Rao bound for unbiased estimators can be written in this way, where now we have n different essays, say. Okay. Now, important question. Is it possible to saturate the Kramer-Rao inequality? Now, let me give you a partial answer to that. Remember that we got the Kramer-Rao inequality by using to this scalar product-like expression and using the Schwarz inequality here, so that we would then get this expression here. So this magnitude square of that is more or equal than the product of the averages of this squared and this squared. Okay? So we use that. Now, for the Cauchy-Schwarz inequality, we know that this inequality can be transformed into an equality if A is proportional to B. Okay? Now, the proportionality constant here, since the integration with respect to psi, the proportionality constant should not depend on psi, but it might depend on x, okay, which is not integrated. Okay? So that's the condition for saturating, and this means that this factor here, A, is proportional to this factor here, so that's the condition for saturating the Kramer-Rao relation. Now, one may say that an unbiased estimator that attains the bound for all x can be found if and only if this condition is satisfied for some functions x estimated that depends on psi and c of x. Okay? So that's a condition. And remember that we are just using that for any p, that means any n. Okay? Now, that's the condition. Now we do something more. We differentiate both sides of this expression with respect to x, and then take the average over the measurement outputs. Okay? Now, on the left-hand side, we are going to have the second derivative of the log, which, remember, is proportional to the Fisher information. And then on the right-hand side, we'll have first the first derivative of Cx times the average of that with respect to experimental data, but the average of that is 0, because this is an unbiased estimator. And then the second term derivative will be Cx times the derivative of the second term, which gives me -1. So at the end, I get that C of x is equal to this, and therefore, this proportionality constant is nothing more than the Fisher information. Okay? Furthermore, you see that if you have a Gaussian distribution for the experimental data, it satisfies this condition with C constant. Okay? Yes. Log of p is equal proportional to x squared, and then you differentiate, so it satisfies this. So this implies that Gaussians saturate the Kramer-Rao inequality with the Fisher information given by the inverse of the width of the Gaussian. Okay? Now, natural question, what if the distribution of experimental data does not conform to that? Huh? We cannot saturate then the Kramer-Rao. Well, we actually can saturate too. And that was shown by Fisher in the limit of a large number of repetitions of the experiment. That's an asymptotic result by using a maximum likelihood estimator. So what is that? So the maximum likelihood estimator is the value of the parameter that maximizes this probability distribution here, or equivalently the log of the distribution. So it can be defined in this way. The maximum likelihood estimator is the argument of p that maximizes p, or that maximizes log of p. So that means that if we have a model-dependent mathematical expression for p, known as the possible as a function of the possible values of the parameter x and also of the experimental results, it is possible in principle to calculate numerically the value of x, leading to the maximum of this expression for a data set, given data set psi. Okay? So that's the game. Now, we can look at this, and in order to understand it better, it's useful to look at it in this way by using Bayes' law. Now, Bayes' law is based on the following simple expression for probabilities. Suppose we have two variables here, like we have in this case, and we want to write an expression for the probability, joint probability of finding one variable with this value psi and the other with the value x. Now we can write this joint probability as the product of the probability of finding the value x times the conditional probability of finding psi if the other variable has the value x. Okay? Now this can also be written in this inverse way, Now here we know the probability that the first variable has the value psi, and this is the conditional probability that the second variable has the value x if the first has the value psi. Okay? So from these two expressions, we get a relationship between the this conditional probability and this one. And in fact, we know that P of psi can be written like that. It's just the integration of this joint probability with respect to all possible values of x. So it can be written in this way. If we assume now that Px is plain, that means we don't know anything about x, then this becomes this expression here, which shows that in fact this conditional probability is proportional to this one. So what I told you before about the maximum likelihood can be translated in the following way. The value of x that leads to the maximum of this distribution that depends on the experimental results is also the value of x that maximizes this distribution here. Oops, I wrote it. No, it's okay, just follow, yeah. So the value of x that maximizes this distribution is the same as the value of x that maximizes this distribution, and therefore it's easy to understand that it's the most probable value of x. Okay? So that's the idea, okay? Given the experimental data. Okay? So since this is true, you see that the maximum likelihood estimator is the solution of this equation here. Okay? So you want to maximize log of the probability distribution. That means that the derivative of the logarithm with respect to x should be equal to 0 for x equal to x maximum likelihood. Also, if you have any identical and independent measurements, then the total probability is just the product of the individual probabilities. We can write the same expression for this complete probability distribution. So that's the condition for determining the maximum likelihood estimator. Now, if we assume that this distribution here as a function of x is narrow enough, then we can expand it around this maximum and neglect these higher order terms. So we get then this expression here. We don't have the first derivative here because it is 0, so the first derivative that shows up is the second derivative. Now, on the other hand, if we have the second derivative of this of this product of probability distributions, this is just the sum of the logarithms. Okay? We can write it like that. And now, if n is very large, this sum can be written as an integral, in fact, as n times the average of this term here. Okay? So it's if you want, the law of large numbers. Okay? So this limit now can be written like that, and this is equal to minus n f of x ml. Okay? So therefore, this is true for the logarithm, of course. This is true for the logarithm. Now we can so what you find then is that when n goes to infinity, p is just the exponential of the logarithm is given by this expression here, which is a Gaussian, by the way. And using Bayes' law, we get for the distribution of x given the experimental data psi, after normalization, this expression here. We just use Bayes' law and write it down like that. So this is a Gaussian, of course. The variance is given by this expression, and we know that this variance should be equal to the inverse of n times the Fisher information. Okay? So you see, so Fisher showed, therefore, that with some assumptions about the probability distribution, that in the limit of high number of realizations of the experiment, you can actually saturate the Kramer-Rao bound for a very simple reason. The reason is that in the limit of many independent experiments, the overall probability distribution becomes a Gaussian, which is related, of course, to the central limit theorem. Okay? So so that's the end of this lecture. What we are going to see in the next lecture is the following. We are going to discuss now the quantum theory of parameter estimation, which leads to the ultimate precision bounds in quantum mechanics up to now, except for the demonstrations with optical interferometry, where we have used quantum states. The general theory up to now was a classical one. So in next lecture, I'm going to do the quantum theory of parameter estimation. I'm going to show you that for some problems, it may lead to analytical expressions or good approximations for the best states. We are going to emphasize the role of entanglement in parameter estimation. And also, we are going to discuss what are the, in general, quite generally, the best states for parameter estimation. From the theoretical point of view, they might be hard to produce experimentally. And we are going to apply the quantum theory of metrology to optical interferometry, atomic spectroscopy, and weak value amplification. Thank you for your attention.